There's a ship called the Seawise Giant. And I know, the name sounds made up, but it was real. It was the largest vessel ever built, 4 football fields long. When fully loaded, it weighed over 650,000 tons. It floated. Not barely. It sailed across oceans for decades. And it was made almost entirely of steel, one of the heaviest materials on Earth. So, how? If you ask most people why ships float, they'll say something like, well, ships are designed to float. Which is true, but it's not an answer. It's just restating the question with extra steps. Some people say it's because ships are hollow. And that's actually closer to the truth, but it still doesn't explain the mechanism. Why does being hollow help? A hollow rock doesn't float. A hollow cannonball sinks just as fast as a solid one. So hollow alone isn't the answer either. The real explanation starts in a bathtub in ancient Greece. And I promise, it's more interesting than it sounds. Around 250 BC, a mathematician named Archimedes stepped into an overfull bathtub and watched the water spill onto the floor. And instead of just cleaning it up and moving on like a normal person, he had a thought. The water that overflowed, its volume was exactly equal to the part of his body that had submerged. Exactly. Not approximately. Exactly. What he realized is this. When you place an object in water, it pushes water aside. It displaces it. And the water doesn't just sit there and take it. It pushes back with a force that equals the weight of the water that was displaced. That upward push is what we call buoyancy. And here's the key. If that upward push is greater than the weight of the object floats.
If not, it sinks. Every single time. No exceptions. Now, take a solid steel ball. Drop it in water. It displaces a relatively small amount of water, just the volume of the ball itself. The buoyancy force is small. The ball is heavy. It sinks. Makes sense. Now, take that exact same amount of steel, same weight, same material, and shape it into a large, hollow bowl. Drop that in water. It floats. Not because the material changed, because the shape changed. The bowl pushes aside a much larger volume of water than the ball did. The buoyancy force is now bigger than the weight of the steel. Up it goes. A ship's hull is essentially that bowl, scaled up to the size of a small city. The interior isn't solid steel. It's a carefully engineered structure of compartments, cargo holds, corridors, and engine rooms, most of which are filled with air. The ship as a whole object displaces an enormous volume of water, way more than its actual weight requires, so the buoyancy force wins. Every time the ship enters the water, it floats. Engineers measure this with something called displacement tonnage, the weight of water the ship pushes aside when loaded. A ship is designed so its displacement tonnage always exceeds its actual total weight. That margin is not an accident. It's calculated to the decimal point for every voyage with every load. Floating is one thing. Not tipping over is a completely different problem. And a ship in the ocean has to deal with waves, uneven cargo, wind, forces constantly trying to roll it sideways.
The solution is ballast, seawater, thousands of tons of it, deliberately pumped into tanks built into the very bottom of the hull. The heavier you make the bottom, the lower the center of gravity, and the harder it becomes to tip. It's why those inflatable punching bag toys always come back upright. Same principle, slightly larger scale. Here's something I didn't expect when I first looked into this. Ships don't float the same way in every body of water. Salt water is denser than fresh water. It pushes back harder. So a ship that's loaded to its maximum safe weight in the ocean, if you sail that exact ship with that exact cargo into a freshwater river, it rides lower. The water is less supportive. Same ship, same load, different result. Naval engineers solved this with something called the plimsoll line. Look closely at the hull of any commercial ship in the world, and you'll find it. A set of marks painted on the steel, each one representing a different condition. TF means tropical freshwater. F means fresh. S means salt. W means winter ocean. WNA means winter North Atlantic, which, if you've ever seen what that looks like in January, you'd understand why it gets its own category. Every voyage, the crew checks which mark applies. They adjust ballast, they calculate.
A ship doesn't just float, it floats within a precisely managed set of conditions that someone has to monitor constantly. The Titanic is the ship everyone goes to when this topic comes up. And people always say, well, it proved that ships can sink, which is true. But what it actually proved is more specific than that. It proved that once you breach the hull and flood the compartments, once the air is gone, the math changes. The buoyancy disappears. And physics, which had been quietly cooperating for years, stops cooperating all at once. Every ship that has ever sunk followed the same logic. The numbers stopped working. The ones still out there tonight, crossing the Pacific, rounding Cape Horn, they're floating because someone made sure the numbers kept working. That's it. That's all it ever was.